My name is Sun. I'm currently a Dixon instructor at the University of Chicago. It's really my pleasure to have a chance to give a series of mini courses at the second Geometric Analysis Festival. I want to thank the organizer for the invitation. So in the following several talks, I'm going to discuss about the topic of uniqueness problem in geometric analysis and the Weyl-Siewicz inequality. The Weyl-Siewicz inequality is a very interesting inequality in real algebraic geometry, and it turns out that it has a widely applications in many other fields, such as geometric analysis. In 1980s, Leo Simon discovered an application of Weyl-Siewicz inequality in geometric analysis, especially in the study of variational problems, and he can use that to prove the certain uniqueness of geometric objects. Later on, there are a lot of application of this work. So in the first part of the talk, I will discuss what is Weyl-Siewicz inequality and its finite dimensional version. And in the second talk, I will discuss Leo Simon's generalization to higher dimension, infinite dimensional case, and how to use it to study some properties of some geometric objects, especially their uniqueness problem. And in the third part of talk, I want to discuss an alternative way, which is directly proof of Weyl-Siewicz inequality for special geometric objects. In particular, I will discuss a joint work with Jonathan Zhu about how to prove that locally the Clifford self-shrinkers are uniqueness among all the self-shrinkers, nearby self-shrinkers of mean curvature flow. Okay, so let's start it in the next video.
Hi, my name is Fabian Rupp. I'm a PhD student at Ulm University in Germany, and I work in the field of geometric analysis, in particular geometric flows of higher order, and especially the Willmore flow and its variants. Let me now draw your attention to this elastic band here, and think of it as a planar curve. What is the difference between this circular curve here and that one? Well, maybe the most obvious one is that the second one crosses itself right here, whereas the first one is embedded. Another thing that you might have noticed is that in order to deform this roundish shape into this figure 8 type curve, I need to invest a certain amount of bending energy. In my talk, I want to discuss the relations between such self-intersecting behavior of planar curves and its bending energy. In the case of the Willmore functional, such a relation follows from a classical inequality by Li and Yao. And in my talk, I want to discuss analogous results for the case of curves in the plane, and I will also present applications for the associated geometric flows. This is a joint work with Marius Müller, who's now in Freiburg. Well, I hope to see you then. Take care.
Hi everyone, I am Alberto Roncoroni, and currently I'm finishing my postdoc at the Department of Geometry and Topology of the University of Granada in the south of Spain, and from April the 1st I will be a postdoc at the Department of Informatics and Mathematics of the University of Firenze in the center of Italy. First of all, let me thank Hugo for organizing the nice festival and for the possibility of deliver these two lectures. So, as you can see, the title of my two lectures is Quantitative Studies of Alexandrov theorem. In the first lecture, I will recall the classical and well-known Alexandrov soap bubble theorem, which is a characterization of constant mean curvature hypersurfaces embedded in the Euclidean space. And I will recall also two classical proofs of this theorem. While in the second lecture, I will move to a quantitative stability result for hypersurfaces embedded in the Euclidean space with almost constant mean curvature. The main result is obtained in collaboration with Giulio Ciraulo from the University of Milano in Italy and with Luigi Vezzoni from the University of Torino, always in Italy. And the result is a quantitative description of the closedness to a single ball for an hypersurface whose mean curvature is close to a constant. Thank you for your attention and hope to see you in the lectures.
Hi, welcome everyone. I'm David Maximo from the University of Pennsylvania. I work in variational problems in differential geometry and also geometric flows. So in this series of videos, I'm going to talk about three manifolds with positive scalar curvature. The goal would be to show you all a recent result I've obtained with Yevgeny Lyukomovich. The first video, basically what I'll do is I'll talk a little bit about the history of this said manifolds. I will discuss the topological classification, and hopefully by the end of the first video, I'll be able to state our result, which basically says the following. So if you have a three manifold with a positive lower bound on scalar curvature, you can construct a one-dimensional graph and a map from the manifold to that graph, such that the preimage of every point of that for that map, it's a surface or a generalized surface of controlled area, controlled diameter, and controlled genus. The area and diameter bound are controlled by the lower bound of positive scalar curvature, whereas the genus bound is a universal bound. So in the second video, I will start discussing the ingredients of the proof. The first ingredient will be minimal surfaces. We use them to decompose a closed three manifold into regions, which we'll call geometrically prime regions. And we're going to reduce the proving the main result to only those regions. And then also in the second video, I'll discuss the next ingredient, which is mean curvature flow, where you can use it and how you can use it to obtain area bounds. Finally, on the third video, we'll use ideas from metric geometry and also from minimal surfaces, filling radius estimates, to show how you can also obtain diameter bounds. So you can adapt the construction from the second video to also obtain diameter bounds. So that's it. I want to finish this video by thanking Roger Lee for the invitation. I hope we were all in Korea, having fun and talking math, but maybe next time. I hope meanwhile everybody stays safe. Thank you.
My name is Jesse Madnick. I'm a postdoc here at the National Center for Theoretical Sciences based at National Taiwan University. Prior to this, I was a postdoc at McMaster University, and prior to that, I was a PhD student at Stanford University. My research focuses on minimal submanifolds and calibrated geometry, particularly those calibrated submanifolds that arise in manifolds with special holonomy, such as G2 manifolds and spin-7 manifolds. In this talk, we're going to discuss a class of minimal surfaces in the round 6 sphere known as holomorphic curves. Now you might ask why I would be interested in the 6 sphere. Well, it turns out that the only spheres that can admit an almost complex structure are the 2 sphere and the 6 sphere. So what we're going to do is equip the round 6 sphere with its standard almost complex structure. That almost complex structure is an isometry for the round metric. And with respect to the standard almost complex structure on the round 6 sphere, we're going to consider an interesting class of surfaces known as holomorphic curves. It turns out that holomorphic curves are automatically minimal surfaces, at least in the round 6 sphere. And so since holomorphic curves are minimal surfaces, you can ask questions such as, what are their Morse indices? Can you get a bound for the Morse index? What can you say about the nullity? These sorts of questions concerned with the second variation of area. So we're going to study the second variation of area, and that is controlled by an operator known as the Jacobi operator. It's a second-order operator. And we're going to study the spectrum of that operator, so its eigenvalues and multiplicities, and we're going to do this in the setting of holomorphic curves in the sixth sphere. Okay, so all of this is interesting in and of itself, I think, but also has applications to the study of associative threefolds in R7, which are important in G2 geometry. Okay, but no background in G2 geometry will be required for the talk.
Hello, I'm Dimitri Kazaris, a postdoc at Duke University. And in my lectures, I will tell you about the notion of total mass in mathematical general relativity. The central fact in this area is known as the very inspiring positive mass theorem. Geometrically speaking, a consequence of this positive mass theorem is the following extremality property of Euclidean space, for instance. It states that there is no compactly supported deformation of the flat metric on Rn, deformed on some compact region, which increases its scalar curvature in this region. No such deformation exists. I will give you two proofs of this positive mass theorem. The first is classical and due to Ed Witten, using spinors. The second is a proof due to myself and some collaborators using certain one-forms or solutions to particular elliptic PDE. There is an interesting relationship between spinors and one-forms that I will also discuss. And in case you have never encountered spinors in your mathematical life so far, I want this to serve as an introduction. So I will be assuming no prior knowledge of these ideas. So I hope to see you all there. Thank you.
I'm Otis Chodosh from Stanford University, and I'll be talking about some new generic regularity results for minimal surfaces in mean curvature flow. I'll discuss the old work of Hart-Simon and some new takes on these sorts of ideas about showing that certain singularities don't occur generically in both area minimizing surfaces, min-max, and in mean curvature flow.
Hello, my name is Min Chen. I'm a graduate student of the University of Science and Technology of China. My main interests are fully nonlinear PDEs, curvature flows, and geometric inequalities. So I will going to talk about how to use curvature flows to prove the Alexandrov feature inequalities on the sphere. I would like to express my gratitude to Huzhou Li for holding this event, and hope you all enjoy this event as well.